Hi, welcome to the Quant Zone. Today we're going to talk about a problem called as coin triplet count. Okay, so in this you have a fair coin, which basically means 50% chance of getting a heads and 50% chance of getting a tails on a random toss. And what we want to know is we want to know what is the expected number of tosses that you need to see a pattern HHH. Okay, that's the first part of the problem. In the next video we're going to be doing another part of this problem. All right, so let's get started with this problem. And before we get started, if you've not subscribed to my channel so far, I would highly appreciate if you could do so. And also share it amongst your friends and family who may be interested in this kind of a content. Thank you. All right, so like we mentioned, in this problem, we have a fair coin, and we want to see a pattern, which is, there are two parts to the question. The first part is we want to see a pattern where we see three consecutive heads, okay, as shown on the screen. And the second part, we're going to investigate the case where we want to see a pattern with one tail and two heads, as shown here, okay? And they have to be consecutive. So I'm tossing a coin, let's say if I get a head first, and if I get a tail, then HTH is not a valid pattern. We need either H, in the first part, we're going to look for HHH kind of a pattern. And the second part, it has to be some tail, head, head. So it can be something like heads, and then a tail, so heads and tail, and then it can be head. Two heads. So this THH is going to satisfy the second part. Okay. What are we saying? We're looking for the expected number of tosses, or coin tosses to be more precise, that we need in order to achieve these, basically the three heads consecutively in the first part, and the second part, we basically need to see the pattern of THH, and we want to know how many, in expectation or on an average, how many coin tosses would we need in order to see this pattern, okay? Okay, so we're going to solve this using Markov chains again because, you see it becomes very easy. Otherwise, it can be a complicated problem, right? All right, so now let's do the first part. So we're looking for three heads, consecutive heads. When we're tossing the coin, we want to know how many coin tosses will we need. Okay, so, one thing to understand is, and let me just have a general discussion before I let you try to give it a first shot at solving this problem, is let's say you had a head, okay, and then let's say you had a tail. Then the pattern becomes HT, okay? And suddenly what you realize is you need, for this pattern to be successful, the first head has to be there, and then another head has to come, and then another head has to come, okay? And you can have something here, it doesn't matter. If it's a head, then this pattern gets successful here itself. But if I talk about the starting position, in starting position you don't have anything here. And let's say if you had two heads, okay, and then you had a tail, then essentially you come back to something what we call as a starting position, right? The reason is because if you had basically heads, and a tail, and then you have another head, then this pattern is still of no use to us because we're looking for three consecutive heads, right? So essentially, if whenever you see a tail here, you're essentially going back to something what I call as a starting position, okay? Okay, so let's now try to build a Markov chain using this concept I just talked about. And I would, encourage you to now pause the video and try to see if you can build up the Markov chain. We've done a couple problems already, so it should be helpful for you to now try to build this up and also try to come up with the transition matrix, which basically indicates the probabilities, and we can then take it from there. Okay, so I hope you got to these the outcomes we were looking for, and if not, that's okay. Let's try to do this together. Okay, so let me say I'm indicating S as a starting position, and again, whenever you've not started the game, it's okay. If at all you see a tail before we see three consecutive heads, we'll essentially bring this in us to the starting position, like we just discussed. Okay, now from a starting position, anytime we want to get three heads, the first step has to be getting the first head. Okay, so we get the first head. And, this is a fair coin. So at any point of time, the probability of heads and the probability of tails is half. Okay, so the probability of heads is half, and that is also equal to the probability of tails at any point in time. Okay, so now what's the probability of going from a starting point to heads? Like I mentioned, it's going to be half because it's a coin toss, and we were saying if you're in the starting position, what's the probability if you get a head? Okay, that's half. Okay, and let's say if we don't get a half, then if we don't get a heads, then basically we get a tails. And like I mentioned, if it's a tails, we go back to our starting position. Okay, so that's why I indicate this via this arrow pointing itself to the starting state. And again, the probability is going to be half, so half here. Okay, now let's try to understand what can be the possible situation in this head. So again, what has happened is you've got a first head. Now there are two possibilities here. Either you get another head or you get a head tail. Okay, now if you get a head tail, you should know that the pattern is violated because we need 3 heads again, right? So essentially this will bring us to the starting position. Okay, so this indicates we go back to starting position, and this indicates we go back, we're gonna stick to head step. Okay, and that's just one step before our final step, HHH. So I hope you got this, what I just said, and if not, I would encourage you to pause the video and try to replay it from this part so that you can understand, what I just said. Okay, so like I discussed, if it's a tails, you go back to the starting position. Again, it's a fair coin, so the probability of going back to the starting position is half. And you could also go to something, what we call as head-head position. And again, the probability of reaching this is half, because when you've already reached here, you've already got one head. And now we're talking about another toss. And in this toss, either you can get the head here, or you could get a tail in HG case, and this will bring us to the starting position. Okay, now let's similarly understand or analyze the HH case. So in HH, either you get a head. So if you get a head, you come to HHH. And as soon as you come to HHH, the game is over. I mean, to say, we want to see HHH kind of a combination, and we saw this, okay? So this is something what I call is the absorption state. It would be an absorption state because we stopped the game there. If you get a tail, okay, so it would be HHT. And now the pattern's violated because you need another 3 heads from here on to get another, to see this pattern, because tails spoils everything. So this will bring us back to the starting point. Okay, so now let's reflect this. So half probability we get HHH, and half probability we go to the starting state. Again, because the moment you have a tails, you get back to the initial state because tail spoils the pattern. And, half is the probability of getting head after you've reached HH. Okay, so this is cool. What about HHH? The moment you are at HHH, what happens? Well, the game is over, like we just discussed. So it will stay to itself with probability 1. Okay, so I think this was the way you can analyze the sequence. Now let's quickly try to build a transition matrix out of it. And I'll represent it like this. Okay, so if you can see the state space here, the state space is nothing but, okay, so basically the state space here is comprised of the starting state, and then you also see something, what I call as the heads, and then you have 2 heads, and then you have 3 heads, okay? And we're going to represent the transition matrix now like this. Okay, so what is the probability if you, now we're gonna just see a few things. So, and I hope this is clear to you, but we're just going to see the transition graph here, and also just confirm the probabilities of going from one state to the other. So the transition matrix basically represents what's the probability of going from state I to state J, and state I's are the initial states, or basically the state which is preceding, and this is the state at which basically our game or our variable jumps to. Okay, and when I say this is probability of starting state, and then staying in that same state. So this is represented by this here, and the answer is going to be half. Now, what's the probability you go from starting state and you head to the, so this we're here, still in this row. In this row here, we're going to be at the starting state initially, and we want to see which states can we jump to, and what are the probabilities associated with those jumps, okay? So from S to stay in S, it was half. From S to go to H, it's going to be half, like we see here in the graph. And for all other states, if you can see, there's no jump, because the only 2 arrows that go from S are here and here. There's no arrow that goes from S directly to HH or from S to HHH. Okay, so therefore we say the probability of going from S to HHH is 0, and from S to HH is also 0. Okay, similarly, you can fill up the rest of the transition matrix. Okay, as you can see, a few things to notice. When you're in H, when you're here, you cannot stay in the same state, because if you have a coin toss, either it's going to be head or tails. If it's a head, you will jump to the HH state. If it's a tails, you go back to the starting state. Okay, so therefore you see probability of being in H and also staying in H is 0, and similar is the case for HH. If you're in HH and you want to stay in HH, that's not possible. In fact, you can also not go back to HH. You either go to starting state if you get a tails, or you go to HHH if you get a heads. Okay, so this is the probability. This is the transition matrix representation. Quick check, all the rows should add up to 1. In fact, they do add up to 1. And HHH is the absorption state. Okay, so this is cool. Now let's try to understand how we can compute the expected number of tosses to achieve them. Okay, now one thing to note is basically our target state is HHH, okay? And this is also the absorption state, absorbing state, by the way, right? So it's an absorbing state. And rest, all of them are transient states, okay? Now, if you remember, in the Markov chains, we discussed equations for expected time to absorption, right? So if you remember the expected time to absorption, okay? So expected time to absorption. Now here you have only one absorption state, which is HHH, and that's cool because we want to see HHH kind of a pattern. We want to reach that state, and we want to understand how much time it's going to take us to reach that state. Now here the time, or each time step, is nothing but a coin toss, right? Every time you flip a coin, you can change the state. That is basically the time. So you can easily use those equations and try to compute the number of expected time to get absorption or to get absorbed, and that is going to be equal to the expected time that is going to be equal to the expected number of coin toss that are needed to see a pattern of HHH. Okay, so again, it's good time that you pause the video and try to come up with these equations and try to solve them. Okay, so I hope you got to the answer, but if not, that's okay. We'll try to solve this together. So again, for absorption states, for absorbing state, mu I, which is again, the expected time to get absorbed while starting in state I, or while in state I, okay, so for absorbing states, mu I is going to be 0 for all I absorbing. The reason is because if you're in an absorbing state, then that means you're already absorbed. There's no time required further to get absorbed, right? It's only for the transient states we'll see something else. So for transient states, okay, mu I is going to be equal to 1 plus sigma j mu j probability of I to j. Now, what is this formula? Again, this is something we've covered in the past. And again, if you've not seen the video, the link isn't going to be in the description. Please do check it out. Otherwise, these problems would be harder to solve and you may not be able to understand much here. Okay. But I mean, they're fairly simple concepts. And if you go through this video, it's going to be very helpful. Okay. So transient state, this is basically expected time to get absorbed from state I. 1 is added for any jump that happens from I to state j. Okay, now what is the state j? Well, it depends on all possible states you can jump to. So j, basically here we span through all of the state space, right? So let me also mark this. J is all states in state space. Okay, and whenever we're trying to find out, okay, from I, what are the possible states you can go to, right? And for each state, we compute the probability of this jump, and we multiply this with the expected time to get absorbed from that state. So essentially what we're saying is we're trying to compute the expected time to absorption from the next state you go to from I, all right? And this state says j, but we don't know the precise state j. Therefore, we compute the probability of reaching any state j, and also multiply it with the expected time to get absorbed from that state j. Okay, so let's try to compute this. Now we know transient states, and I'm represented by TS, are S, H, 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 right? These are the only states that are transient. Because if you see here in the graph, or in the state space, S is here, H is here, HH is here, and these states are fine. But HHH is where you see no outgoing arrows and everything just points to itself with a probability 1. That's an absorbing state. Okay, so let's compute this. For probability mu s, this is 1 plus mu s, probability of ss, plus mu h, probability of sh, plus mu hh, probability of shh. Okay, now if you go back to the transition matrix, what you see is there are a few things in the first equation. First is these probabilities are 0, so s, you can't go to h, or hhh. Okay, then second thing is the absorption, expected time to get absorbed from an absorption state is 0, right? So mu hhh is 0. Okay, so let's see what we can cut out, and we got to also add the last state, hhh, probability of S to HHH. Okay, because we have to consider all the states in the state space, and what you see is this becomes equal to 0 because mu H is 0, and probability of S to HH is 0. This will also be 0, and because you see here, right here, you can't jump from S to, you can only go from S to S or to H, but you can't go to HH or HHH, right? As you can see on the graph here as well. All right, so this equation basically boils down to mu S is equal to 1 plus mu S by 2 plus mu H by 2. And these are probably then just picking up from transition matrix. You can confirm the answer or confirm these equations. The final probability equation becomes mu S by 2 plus, mu S by 2 minus mu H by 2 minus 1 or is equal to 1, right? That's equation 1. Let's talk about the second equation for transition state. Mu H is 1 plus mu S times HS plus mu H times PHH plus mu HH times PH to HH plus mu HHH times probability of H to HHH. Okay, so again, I hope this is clear. Now we're in state H, and we're trying to compute all the possible states we can jump to, and also, just simply application of the formula. So again, this will be 0 because mu HH is 0, and basically the probability of jumping from H to HHH is also 0. This is, we shall have this. This one is 0 because the probability of being in H and also staying in H is 0. Okay, and like I mentioned, the probability of going from H to HHH is also 0, right? It's only half for the other two states. So use this. Okay. Okay, you get the second equation. You can rearrange this. All right, and the third equation is mu HH is 1 plus S. Okay. I hope the substrate is clear. This is HH going to H. And if you go to this row here in the transition matrix, what you see is from HH, you can either go to HHH or you can go to starting state. So both of these things are 0. Okay. So what we see is basically from H, you can't go to H. This is going to be 0. You can't stay in HH. This is going to be 0. And this is also going to be 0 because mu HH is 0. As we mentioned here, in the absorbing state, the expected time to get absorbed is 0. So this equation becomes mu HH is equal to 1 plus, this is 0, this is 0, this is 0, mu S by 2. Okay, so if you solve this further, this is mu S by 2 minus mu HH. Okay, so we have 3 equations, 3 variables, and we'll try to solve this using something called a row reduction method. And you can, this is simple 3 equation, 3 variables. You can also use equations to solve them, but I'm just going to use, row reduction method. That's a linear algebra trick, and it's a method basically, and it just helps us to avoid mistakes. Okay, so basically what I've done is I've mentioned the coefficients of mu S, mu H, and mu HH. And this is the RHS coefficient. Okay, so if you see in equation 1 here, the coefficient of mu S is half, the coefficient of mu H is minus half, and the right-hand side coefficient is 1. And if you go back to our matrix, coefficient of mu S is half, coefficient of mu H is minus half, mu HH is not present, so the coefficient is 0 in other terms, and RHS coefficient is 1. Similarly, for the last equation, you see it's half for mu S, mu H is not present, so coefficient is 0, for mu HH it's minus 1, and the right-hand side is minus 1. Let's try to solve this using row reduction method. Okay, so what we want here is basically we want an order of coefficients in which you have, an upper triangular matrix, right? So essentially what we want is these numbers here can be non-zero. But most importantly, this coefficient, this coefficient, this coefficient should be non-zero. And these coefficients here should be 0, because then it will be an upper triangular matrix, right? So this is what we were trying to get. And again, this is a step of the method in which you'll see it easily helps us to come up with the answer. So this time I have a non-zero coefficient here, I have a zero coefficient here and also here, but I want to have a zero coefficient here as well, because then it will turn it into an upper triangular matrix. And whatever operations you apply here, you also have to apply on the coefficients here, right? So therefore you get some coefficient what we see here. So I don't know. Okay, so that's cool. Now what you see is you see mu h. If you remember here again, the way in which coefficients were written was mu s, mu h, mu hh. Okay. So now mu hh becomes minus half times mu hh. The coefficient is multiplied; it becomes equal to minus 4. This implies mu hh is 8. Okay. Then you have mu, and I'll just write the coefficients, here. Basically the variables here for the sake of convenience. It's mu h, okay, and RHS coefficient. So naturally what this means is, mu hh times this, if you see the last row, how I interpret it is the coefficient times this variable is equal to this. Okay, so this is the equation. Simplified equation, directly get mu hh right away. Let's now compute the mu h. So we know half times mu h plus half times mu hh is minus 2. Okay, so therefore, if I multiply it with 2, or with minus 2, I get mu h minus mu hh is 4, right? I just multiplied by minus 2 on both sides. So mu h becomes equal to 4 plus 8, which is 12. Okay, let's now try to compute mu s. So mu s is, again, if you see this matrix here, I'm just going to be multiplying coefficients with the variables here. Okay, and then I equate it to RHS. So this is mu s by 2 minus half mu h by 2 plus 0 times mu hh. That's going to be equal to 1. So this goes away. This becomes equal to mu s minus mu h is 2, just multiplying both sides with 2. So mu s becomes equal to mu h plus 2, and that is equal to 14. Okay, so we have all the answers. Since mu s is 14, mu h is 12, mu hh is 8. Okay, what is this? This is basically telling us the expected time to get absorbed when you are in state I. This is what the definition of mu I is. And if we go back just to show you here again, okay, expected time to get absorbed when you're in state I. This is a general definition. Now for absorbing state, this is 0, and transient states, we have this. Okay, so essentially we were looking for expected time or expected number of coin tosses that we needed to reach this absorption state, or get absorbed in other terms. So we are talking about the starting state. So the answer here is going to be mu s, which is 14, because that is the expected time to get absorbed from your starting state. And now expected time here implies 14 coin tosses is what we expect to have, in order to see this pattern HHH. Now, it does not mean if you toss it 14 times, you're going to get HHH. It's just an expectation, right? There is going to be some variation here. Sometimes it can be more than 14, sometimes it's going to be less than 14, okay? So I hope you got this answer right. If you did, that's perfect. That's amazing. One of the trickier questions, but look how easy Markov chains made it, right? So I hope you enjoyed this video. In the next one, we're going to do the second part. All right, so I hope you enjoyed this video. And if you did, please give it a like, and also share your experience in the comments. And also, if you've not checked out my playlist on brain teasers, it's a fantastic resource which is coming out to be covering all the different kinds of brain teasers which you may encounter in your next quant interview. So thank you for your time, and thank you for your attention, and see you next time with another problem.